In this video, we are going to talk about linear independence, which is a really important topic in linear algebra and one you should become very familiar with. And in fact, you should memorize the definition of linearly independent, but fortunately, it's a very easy definition to remember. So if you have vectors v1, v2 up to vp, then if this vector equation x1 v1 plus x2 v2 plus xp vp equals 0 has only the trivial solution, so that means there's no linear combination that equals 0 except for the trivial solution. That's what it is to be linearly independent. To be linearly dependent, that means there is a solution that's not the trivial solution where you can take a linear combination and get the 0 vector. And we're going to look at this more, but again, this definition is one you should memorize. Looking at this vector equation form, we can look at the matrix form of this. So we take the columns of v1, v2, and vp up to vp, and we make a matrix A, and we take the coefficients x1, x2 up to xp, and we make the vector x, and then we set it equal to the 0 vector. So now, linear independence of the matrix columns, so of the columns of matrix A, they're linearly independent if and only if the equation ax equals 0 has only the trivial solution. We will look at the special case of one or two vectors. First, if there's only one vector. This is linearly independent if and only if, that's what the IFF is, if and only if v is not the 0 vector, because if we have x1 times v, remember v is not equal to 0, is equal to 0, that must mean x1 has to equal to 0, and that's the only possibility, x1 equals 0, so it has only the trivial solution. The 0 vector 0 is linearly independent because x1 times 0, well, no matter what x1 is, it's always equal to 0, so there's many non-trivial solutions. The second special case is two vectors, and two vectors are linearly dependent, or the set is linearly dependent, if and only if at least one of the vectors is a multiple of the other, and we'll do an example of that. And then we have basically our sets of two or more vectors, and we have this characterization of linearly dependent sets. An index set of vectors, v1 up to vp, of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. This is something I will add more on once we finish this overview slide. And then we'll look at two more theorems. If a set contains more vectors than there are entries in each vector, then the set is linearly dependent. And second, if a set v1 up to vp, a set of vectors, and Rn contains the 0 vector, then the set is linearly dependent. And I wanted to say a word about linearly dependent sets. And if it's linearly dependent if at least one of the vectors is a linear combination of the others. In a previous video, I had told you that I like to think of these vectors as sort of like tinker toys, linear algebra tinker toys that I don't think any child would want to play with, but we're going to talk about it anyway. So we have these building blocks, and these are vectors, and the direction they point cannot be changed. But they remind me of the sticks in tinker toys. And you have tools to scale vectors, just like with tinker toys, you have different lengths of the sticks. So you have tools to scale the vectors. They can lengthen, shorten vectors, or make them point in the opposite direction if they're negative. And then you have these connectors, just like in tinker toys. And so you can combine two vectors using vector addition. So from two vectors, so this is a different kind of connector than what you have in tinker toys though, but you put in two vectors and then you'll magically get a third new vector, and it combines using the rules of vector addition. I had then mentioned if you had a set of these tinker toys, the span was the set of vectors you could make. So for example, if all the tinker toys you had all pointed in the same direction, let's say they all pointed to the right, there's no way you could plug them into your vector addition and get a vector that pointed upwards or even, at a 45-degree angle. So the span of just these two vectors, well, you could scale them and you could add them together and you could point them in the other direction, but the span is just vectors that point somewhere along this line, that's on this line pointing in either direction. So it's not a very powerful set of tinker toys. But anyway, that was the idea of span. And now we have this idea of linearly deep or linear dependence. So if you have two tinker toys, let's say one points to the right and one points straight up, then you can add them together and you can get this vector here. And so these two, this vector here, because it's a linear combination or can be made from these other two vectors, is dependent on these two vectors. So the idea of linear dependence, if a vector is linearly dependent on a set of other vectors, that means it can be made from the other vectors. And so that's exactly what this is saying, that it's linearly dependent if and only if at least one of the vectors is a linear combination of the others. In other words, one of the vectors can be made from the other. So the idea of linearly independent, that means the set of vectors you have can't be made from one another. So the idea is if you have two linearly dependent vectors, they aren't going to be as interesting a set. They're not going to be able to make as much as two linearly independent vectors. So that's something that we want to talk about. So when they're linearly independent, they can't be made from one another. In other words, they're sort of unique in their way, and you can't replace one with the other. Whereas if you have, again, our linearly dependent vectors, in this case, this vector, it actually can, if you got rid of it, you'll still be able to make just as many vectors with these two, because this vector sort of has repeated information. So because it's dependent on the information that these two vectors have. So that's kind of my intuitive sense of tinker toys and linear algebra. But the thing I would have you get from that, if it's dependent, that means at least one of the vectors can be made from the other. Whereas if it's independent, they can't be made from one another. And also, how do you make one? You use a linear combination. So if it's dependent, in other words, there's a non-zero solution to this the homogeneous equation, which means then, let's say this is the vector that you can make with the other ones. You can solve for V1 by moving all of these terms over to the other side and then dividing everything by C1. And that'll give you V1. So V1 will be dependent here. Whereas if it's linearly independent, you only have zeros here, so you can't make one vector from another in the way you can with this equation. So those are the ideas hopefully you want to keep in your head when we talk about linearly independent. Now we're going to back up and come back to the strict definitions, which you should have memorized. So to be linearly independent, then this vector equation x1v1 plus x2v2 plus xpvp equals 0 has only the trivial solution. So to get a linear combination equal to 0, all the coefficients has to be 0. To be linearly dependent, that means there are coefficients that are not all 0, such that this linear combination can equal to 0. For our first example, we'll let v1 equal 1, 2, 3, our second vector equal 4, 5, 6, and our third vector equal 2, 1, 0. We want to determine if this set of vectors is linearly independent. And if possible, find a linear dependence relationship among v1, v2, v3. To answer this first question, are they linearly independent? We're going to use the definition of linearly independent. So we want to look at the linear combination of x1v1 plus x2v2 plus x up to xpvp. So that's what I've written here, and I've plugged in my v1 times x1, my v2 times x2, and my v3 times x3 is equal to my 0 vector, 0, 0, 0. Again, just taking from this definition. And remember, this vector equation, it has a corresponding matrix equation, which has a corresponding system of linear equations. So their solutions are equal. So I have the matrix of my column vectors, 1, 2, 3, 4, 5, 6, 2, 1, 0, and then my solution, my B vector, 0, 0, 0. I row reduce it until I get to 1, 0, 0, 4, 1, 0, 2, 1, 0, and 0, 0, 0. And what I find here with this last row, that x3 is free, and x2 will equal to negative x3, and x1 will equal to 2 times x3. And what that tells me is there's an x1, x2, x3 where they're not all equal to 0 that will solve this equation. That means there's a non-zero solution, so they are linearly dependent. And I wrote that here. It's linearly dependent since we have the solution, well, here we have for x1, 2x3. For x2, we have minus x3, and then we have, for x3, we have x3, which is equal to 2 minus 1, 1 times x3. And that is our non-trivial solution. And this is the answer, it's linearly dependent, to our first question. But I thought I would just go ahead and say then, let's let x3 equal 1. So 2 minus 1, 1. Let me demonstrate to you that this is indeed, or verify for you that this is indeed a solution. So I'm going to plug in 1, 2, 3. My vector 1, 2, 3, I'm going to plug in 2. And then I have my 4, 5, 6, and I'm going to plug in negative 1. So that's negative 4, 5, 6. And then I'm going to have my 2, 1, 0 times my x3, which is 1. So I just kind of have a 1 out here. When I do this multiplication and then add everything together, I do get the 0 vector. And now we're ready to look at part B. If possible, find a linear dependence relation among V1, V2, V3. In other words, we want to write V1 as a linear combination of V2, V3, or it could be that V2, we write that as a linear combination of V1, V3, or we could write V3 as a linear combination of V1, V2. You can take your pick. But when I look at this, this has no negatives and it has no coefficients. I might write V3 as a linear combination of 1 and 2. And just looking here, so I can have 2, 1, 0, I can then add this 4, 5, 6 to both sides of the equation. So it gets rid of this or cancels this. And over here to 0, I get 4, 5, 6. And then I can subtract 2 times 1, 2, 3 from both sides of the equation. I get minus 2 times 1, 2, 3. And then you can verify that indeed 2, 1, 0 is a linear combination of 4, 5, 6 minus 2 times 1, 2, 3. So 2, 1, 0 is dependent on 4, 5, 6 and 1, 2, 3. And to be honest, really you could have solved for any one of these three vectors. I just chose to solve for V3. But you can say V1 is dependent on V2 and V3, or you could say V2 is dependent on V1, V3. I have the last example kind of summarized here. Obviously, it doesn't have all the steps, but it's there for your reference. But now here in our example, we've been talking about the vector form of the equation, but we can also look at the matrix form. So here is a vector form of the homogeneous equation, x1, a1 plus a2, x2, a2 up to xn, an, where a1, a2, an, they're vectors. So what we can do is then write A, our matrix, as being the matrix a1, a2, up to an. And each of these, again, are vectors. So then the matrix form of our equation is going to be A times x, where x is x1, x2, the vector containing x1, x2 up to xn equals 0. And what this is saying for the matrix equation, that for the matrix, the columns of the matrix A, that is the columns being a1, a2 up to an, are linearly independent if and only if the matrix equation ax equals 0 has only the trivial solution. So these are equivalent statements, so you should take a look at it and convince yourself that is so. And we will do this next example. Our matrix A is equal to 0, 1, 5, 1, 2, 8, and 4, negative 1, 0. Determine if the columns of matrix A are linearly independent. If the column vectors of A are linearly independent, I can look at this as a linear combination of the column vectors and say the homogeneous equation has only the trivial solution, or I can use this theorem here that says the columns of matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. Both of these systems have equivalent solutions as this matrix using this augmented matrix. So we're going to use 0, 1, 5, 1, 2, 8, 4, negative 1, 0, 0, 0, 0. Row reduce that to get 1, 0, 0, 2, 1, 0, negative 1, 4, this is a 13, and 0, 0, 0. And what that tells us is 13 times x3 is equal to 0. In other words, x3 must equal to 0. Then we're going to get x2 equals to 0 and x1 is equal to 0. So in other words, this vector equation has only the trivial solution. Also, the matrix equation has only the trivial solution. And by the definition of linearly independent, only the trivial solution means that the vectors, the three vectors, are independent. So we've talked about the definition of linearly dependent and independent. We also related that both to the vector homogeneous equation as well as the matrix homogeneous equation. Now we'll talk about the special cases of sets of one or two vectors. And I just cleared out some space and moved the statements here. So a set of one vector is linearly independent if and only if the vector is not 0. Because if v is not equal to 0, then in order to get a scalar times v equal to 0, that scalar must equal to 0. And that's the only way you're going to get the 0 vector if v is non-zero. So that means it has only the trivial solution. Only the trivial solution means it's independent, which is exactly what this statement says. The next one, the 0 vector, we denoted with the bold 0, is linearly dependent because if we look at the equation x1 times the vector equals 0, that has infinitely many non-trivial solutions. x1 can be any scalar, and as long as you're multiplying by the 0 vector, you can get the 0 vector, infinitely many solutions. Two vectors, v1 and v2, are linearly dependent, or the set is linearly dependent. I'm just laughing because I always look at this and think of it as two vectors, and I think the verb should be are, but it's because it's the set of vectors is linearly dependent if and only if at least one of the vectors is a multiple of the other. I put a note here that the IFF means if and only if, but now to look at the statement about the two vectors, they're linearly dependent if and only if at least one of the vectors is a multiple of the other. To see that, I wrote this out. So we have x1 v1 plus x2 v2 equals 0. And we're saying they're dependent. So x1 and x2 are not both 0 because there's a non-trivial solution if it's dependent. And for the sake of argument, let's just assume x1 is equal to 0. If it's x2, the argument's sort of the same, symmetric. So if x1 is not equal to 0, well, first the first thing we can do is subtract x2 v2 from both sides of the equation, and we get x1 v1 is equal to x2 v2. And now, since x1 is not equal to 0, we can divide both sides of the equation by x1, and we get v1 is equal to x2 minus x2 over x1 times v2. And this here is just another scalar. It's just another real number. So here we have v2 then, or v1, is a scalar multiple of v2, which is exactly what this is saying here. If they're linearly dependent, then you can make this calculation and see that they're multiples of the other. I have an example here to determine if the following sets of vectors are linearly independent. My first set of vectors is v1 equals 3, 1, and v2 equals 6, 2. My second set of vectors is v1 is equal to 3, 2, and v2 is equal to 6, 2. For my first set of vectors, since v2, which is equal to 6, 2, is equal to 2 times 3 times 1, which is 2 times v1, then v1 and v2 are scalar multiples of each other, and by this property here, this statement here, they are dependent. And in fact, you can write out the linear combination that gives you 0. So if you take 6 equals 2 times 3, 1, then you can move this to the other side of the equation, so you get 6, 2 times 1 minus 2 times 3, 1 equals 0, 0. So here is your x, your non-trivial solution is 1, negative 2. So they are dependent, and they are two collinear vectors. So this is, the blue is my 6, 2, and the black vector here is my 3, 1. For my second set of vectors, 3, 2, and 6, 2, note that 3, 2 is not a multiple of 6, 2, and by this theorem here, because it's an if and only if, that means they're independent. And we can graph them. You can see V1 has this direction, V2 has that direction. So there's no way you're going to be able to change the direction of V1 into V2 or V2 into V1. You only have two vectors. There's nothing you can add to get a different direction. And the other thing you can do to verify, this is kind of intuitively, you can't, they're independent. You can also go back to your definition to verify they are independent. In other words, you can look at 3, 2, and 6, 0, and the homogeneous equation 0, 0. You can see that this augmented matrix reduces to 1, 0, 2, 1, 0, 0, which means x2 is equal to 0 and x1 is equal to 0. That is the only solution. Only the trivial solution exists, and therefore they are independent. So again, you can use this statement here, or you can just go back to the definition and verify that. Next, we can look at characterizing a set of linearly dependent vectors. So I cleared some stuff out here and I moved up my definition to make more room. So we can characterize linearly dependent sets by this statement. An index set S, V1, V2 up to Vp of two or more vectors, is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In my tinker toy kind of analogy, the idea of making one of the vectors is a linear combination of the others corresponded with being able to make one of the vectors from the other vectors. The statement goes on and it says, in fact, if S is linearly dependent and V1 is not 0, then some Vj, with j greater than 1, is a linear combination of the preceding vectors. And we'll look at an example of that in just a minute. But I have one other note, because this last statement, this theorem does not say that every vector in a linearly dependent set is a linear combination of the preceding vectors. And again, we'll look at that, an example of that in just a moment. Here's an example. Describe the set spanned by u and v and explain why a vector w is in the span uv if and only if uv and w are linearly dependent. So we have u is equal to 3, 1, 0 and v equals 1, 6, 0. And we're going to start by describing the span of u and v. Since u and v are not scalar multiples of each other, then the span of uv is going to be a plane. And I think we illustrated this in a previous video when we talked about span. So in other words, if we have all linear combinations of u and v, then you're going to get a plane. And I'm also just going to note back to our previous statement when we had two vectors. They're linearly dependent if and only if at least one of the vectors is a multiple of the other. Since they are not multiples of each other and this is an if and only if statement, that means they are not linearly dependent, meaning they are linearly independent. Now we can go on to part B that says W is in the span of UV if and only if UV and W are linearly dependent. I'm going to start by rewriting this statement. So W is in the span of UV. So W is in the span of UV if and only if. So I'm going to write this biconditional, this if and only if with the arrows. UVW is linearly dependent. So this is what I'm trying to prove. And this if and only if means we have two directions to prove. We have the forward direction as kind of reading this arrow in this direction, which is W is in the span of UV implies UVW are dependent. And then we have the backwards direction, reading the arrow this way, which UVW are dependent implies that W is in the span of UV. And I also have these forward and the backward direction arrows here to remind us. I am going to start with this forward direction. W is in the span of UV implies that UVW are dependent. So W is in the span of UV. That is given to us. That's our hypothesis. What that means is W is equal to X times U plus X2 times V. That's just the definition of what it is to be in the span. To be in the span means that W is a linear combination of UV. Well, this means here that W is dependent on UV, which means that UV and W is a linearly dependent set. So we've proved the forward direction. Now we need to prove the backwards direction, that UVW being dependent means that W is in the span of UV. And I have cleared up some space, moved my backwards direction arrow here, and I start with UVW are dependent, and that is given. That's my hypothesis. If they're dependent, that means there's a linear combination with x1, x2, x3 not all equal to 0, a non-trivial solution. And we are going to assume x3 is not equal to 0. It's symmetric. You could assume x1 or x2 are not equal to 0. The argument would be the same. So we're just going to assume x3 is not equal to 0. Then what I can do is I can isolate my wx3 by moving the other two terms to the other side. I should have put negatives here. And then I can divide by x3 since x3 is not equal to 0. And this is just algebra. And this statement here is the definition of W being in the span of UV, because W is a linear combination now of U and V. This negative can go with the x1 over x3, and this negative can go with the x2 over x3. So now W is in the span of UV, and I have proven what I wanted to show. Now we are down to our last theorems. The first theorem says if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. That is, any set v1, v2 up to vp and rn is linearly dependent if p is greater than n. I'm going to start by making a matrix A from the vectors v1, v2 up to vp, and they're in rn. So in other words, v1 looks like this. It has n entries, n coordinates, and then there are p vectors. So A is an n by p matrix. Remember, it's always rows, columns. The number of rows, that's the number, that's going to be n. The number of columns, well, there are p vectors, so that's the number of columns. Relating this to our matrix equation, our homogeneous matrix equation, Ax equals 0 corresponds to a system of n equations with p unknowns. And p in this case is greater, the number of unknowns is greater than the number of equations. Since there are more variables than equations, you don't have enough equations to determine each variable, so there's going to be at least one free variable. Hence, Ax equals 0 is going to have a non-trivial solution, and the columns of A, therefore, are linearly dependent. An example of using this theorem: determine if the three vectors below are linearly dependent or independent, and the vectors are 2, 1, 4, -1, and -2, 2. In this case, to use this theorem, I'm going to form my matrix of these with these as my vector columns, and it's going to be the homogeneous equation, so I'll have 0, 0 at the end. So I have 2, 1, 4, -1, 2, -2, 2, and 0, 0. So here I have two equations and 1, 2, 3 unknowns. So n is equal to 2, p is equal to 3. So according to this, p is greater than n, so therefore I must have a non-trivial solution, and the set is dependent. So we have answered this question, and I kind of summarized our answer up here because I want to show you how they are dependent. So I took my matrix A here, I row reduced it until I got 1, 0, 0, 1, 1, -1, 0, 0. So from here I get x3 is free, x2 is equal to x3, and x1 will be equal to -x3. So our solutions are of the form, well, I have a -1, 1, 1 times x3. And in fact, so I went ahead and plugged in -1, 1, and 1 as my scalar multiples for my three vectors. So I have 2, 1 times -1. I have my 4, -1 times 1, and my last vector, -2, 2 times 1. And you know, I could have multiplied it by any multiple of -1, 1, 1. Like -10, 10, 10 would have worked, or -5, 5, 5 would have worked, or 0.08, -0.08, 0.08, 0.08 would have worked. But I did the easy one, which is just 1. Okay, and you can see that it's equal to 0, 0. So it does have a non-trivial solution, which is right here. And then the other thing is, now I can write any of these vectors, but because this has a 1 in front of it, I don't know why, I just chose this one. So what I did is I chose to move this to the other side, so I get 2, 1 is equal to 4 minus 1 plus negative 2, 2. So I can write one equation in terms of the other two, one vector in terms of the other two. So the other thing to note is none of these three vectors are scalar multiples of each other, and yet they are linearly dependent. And I wanted to come back to this characterization of linearly dependent sets. So we said that a set of vectors of two or more vectors is linearly dependent if and only at least one of the vectors is a linear combination of the others. So here we see we have one vector is a linear combination of the others. It's dependent. The second fact is the second statement is what I wanted to focus on now. If S is linearly dependent and V1 is not equal to 0, so here V1 is not equal to 0, then some Vj with j greater than 1 is a linear combination of the preceding vectors V1, V2 up to Vn. So here I can write V3 as a linear combination of these other two vectors. 2, 1 minus 4 minus 1 will give me V3. So V3 is a linear combination of the preceding vectors. The note is the theorem does not say every vector is a linear, in a linearly dependent set is a linear combination of the preceding vectors. So in other words, V2 is obviously not a scalar multiple of V1, and therefore V2 is not a linear combination of V1. So it's not that every vector is a linear combination of the preceding vector. It's just that you can solve for the last vector in terms of the other vectors. And in fact, you can solve for any one of these vectors in terms of the other two. But this last statement is you can always solve for the last vector in terms of the preceding vectors if they are linearly dependent. Now we are up to or down to our last theorem, which says if a set V1, V2 up to Vp and Rn contains the 0 vector, one of these is the 0 vector, then the set is linearly dependent. For my proof, I'm going to let V1 equal 0. It could, it's symmetric. Any one is equal to 0, but one of them is equal to 0. Then I have my linear combination equation, x1v1 plus x2v2 plus up to xpvp equals 0. So these are going to be linearly dependent if there exists a non-trivial solution. And in fact, because v1 is equal to 0, x1 could equal to anything. So I'm going to concentrate on the solution, the non-trivial solution, where x1 is equal to 1. And all the other multiples, the scalar multiples or coefficients, are going to be 0. So x2, x3 up to xp is 0. But x1 will be equal to 1. And again, that could be any real number. And that will be my non-trivial solution, showing me that this is linearly dependent. This next example is to determine by inspection if the given set is linearly independent or dependent. So the first set is 176, 209, 315, 418. The second set of vectors is 235, 000, 118. And the last set of vectors is negative 2, 4, 6, 10, and 3, negative 6, negative 9, 15. I have all of these different definitions and statements and theorems here that you might want to take a look at to use. We will start with this first set of vectors where V1 is 176, V2 is 209, V3 is 315, and V4 is 418. We are going to use this theorem here where we have a set containing more vectors than entries in each vector. That is, we have p vectors in Rn. So here we're in R3 because we have an x, y, z coordinate. So n is equal to 3, but we have p vectors. That is, we're going to have 3 equations and 4 unknowns. We have more unknowns than equations, which means we're going to have a non-trivial solution, and these vectors are dependent. Looking at part B, where V1 is equal to 235, V2 is 000, and V3 is 118. In this case, we are going to use this theorem here. So if we have a set of vectors and it contains the 0 vector, then the set is linearly dependent. since we have the 0 vector, we can say it is dependent. And I went ahead and I wrote, because this actually doesn't take much calculation at all, we can multiply our first vector by 0. Our second vector, the 0 vector, can be multiplied anything. I chose to multiply it by 2. Our third vector then is multiplied by 0. But here we have a non-trivial solution, 0, 2, 0. So it is dependent. For our last set of vectors, v1 is equal to negative 2, 4, 6, and 10, and v2 is equal to 3, negative 6, negative 9, 15. For these two vectors, we're going to use this special case up here concerning two vectors. They are linearly dependent if and only if at least one of the vectors is a multiple of the other. So I noted that negative 2, 4, 6, 10 is equal to negative 2/3, 3, negative 6, negative 9, negative 15. Therefore, they are dependent. Before we do our last set of problems, I'm going to review what we have talked about in this video concerning linear independence. First, we did the definition. We said that a set of vectors is linearly independent if the vector equation x1v1 plus x2v2 plus xpvp equals 0 has only the trivial solution. They are linearly dependent otherwise. In other words, if this linear combination set equal to 0 has a non-trivial solution. This definition talked about linear independence in terms of a vector equation, but we can convert that to a matrix equation. So the columns of a matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. The next thing we did is we looked at special cases of sets of one or two vectors. So a set with one vector is linearly independent if and only if v is not the 0 vector. And that is because the equation x1 times v equals 0, if v is not equal to 0, that will force x1 to be 0. So that is the trivial solution, and that is the only solution. Next, the 0 vector is linearly dependent because x1, 0 equals 0 has many non-trivial solutions. Any real number x1 here will solve the equation. Last, the two vectors v1, v2 are linearly dependent if and only if at least one of the vectors is a multiple of the other. We went on to look at two or more vectors, and we had this theorem that characterized linearly dependent sets. So an index set v1 up to vp of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. And in fact, if S is linearly dependent and v1 is not 0, then for some vj with j greater than 1, it will be a linear combination of all the preceding vectors, v1 up to vj minus 1. With this idea, we know that if vectors are dependent, then one of the vectors can be written as a linear combination or can be made from the other remaining vectors. Last, we had two more theorems. If a set contains more vectors than there are entries in each vector, then the set is linearly dependent. That is, for p vectors in Rn, they'll be linearly dependent if p is greater than n. There are more unknowns than there are equations. This last theorem, if a set S contains the 0 vector, then the set is linearly dependent. I have another set of problems, and because we've covered all the material, I'm going to suggest that you try all the problems on your own before continuing in the video to see the solution. I will keep the definition of linearly independent and linearly dependent up here for your reference. The first problem is u is equal to the vector 3, 2, negative 4, v is the vector negative 6, 1, 7, w is the vector 0, negative 5, 2, and z is the vector 3, 7, 5. Are the sets uv, the set uw, the set uz, the set vw, the set vz, and the set wz each linearly independent? Why or why not? For each of these pairs, since they're taken two at a time, I used this statement here from our overview sheet that said two vectors, the set of two vectors, v1, v2, are linearly dependent if and only if one of the vectors is a multiple of another. And it turns out none of these are multiples of the other, and I will show you the first three why that's the case or how I know. And then since they aren't, that must mean that they are independent. So the answer is yes, all the sets are independent. So let's look at u and v, where u is 3, 2, -4, and v is -6, 1, 7. If we focus first on the first coordinate, here, to get from 3 to 6 to -6, you'd have to multiply by a scalar of -2. However, for the second and third coordinate, -2 will not work for either of them. So there's not one single scalar you can multiply this first vector to get the second vector, or vice versa. If we look at u and w, that is if we look at 3, 2, and -4, and w is equal to 0, -5, 2, you can see for the first coordinate, we'd have to multiply our 3 by 0. But then, if we multiply 0 by 2, we're not going to get -5. So there's no single scalar that you can multiply this vector to get this vector here. Looking at uz, we have 3, 2, -4, and then z is 3, 7, -5. So here, the first coordinate would suggest the scalar would be 1. However, the second coordinate, the scalar 1, wouldn't work on the third coordinate either. So there's no one scalar you can multiply u by to get z. So they are independent. Similarly, you can find vw, they are not independent, right? Because here you'd have to multiply -6 by 0 to get this first one, but you can't use that for the second or third coordinates. Here you have 6, 1, 7, and 3, 7, 5. Here you would have to multiply your -6 by -1/2 in order to get 3. But -1/2 times 1 would give you -1/2, which is not equal to 7, so they're not independent. And for wz, the 0, 5, 2, and the 3, 7, -5, here you would have to, there's nothing, well, you could multiply 3 times 0 to get 0, but then you can't multiply 7 times 0 to get -5, so they are also independent. This next problem uses the same four vectors, u, v, w, and z. We found that these pairs are all independent. So does that answer here imply that u, v, w, z, the four vectors together, are linearly independent? And the answer is, while the four vectors may be linearly independent, these two pairwise, the pairwise independence does not guarantee this. So the answer is no. It's not sufficient evidence to say that they are linearly independent. While we know, for example, that u cannot be made just by scaling v or w or z, what we don't know is that possibly u could be made by a linear combination of v and w, or a linear combination of w and z, or a linear combination of v, w, and z. The next question also refers to the same four vectors to determine if u, v, and z is linearly dependent. Is it wise to check if, say, w is a linear combination of u, v, and z? If you check and w is a linear combination of u, v, and z, then you can say that the set u, v, w, and z is linearly dependent. However, if w is not a linear combination of u, v, and z, you cannot conclude whether or not the combination u, v, w, z is linearly dependent or independent just based on the previous information that they're pairwise independent. So the answer is not really. It's not really wise if you're only going to check w. And the final question with these four vectors u, v, w, and z is the set of four linearly independent? To answer this question, I set up my matrix, my 3, 2, -4, 6, 1, 7, 0, negative 5, 2, and 3, 7, negative 5, my matrix A times X equals 0. And to find if it's linearly independent, I want to know if there's a non-trivial solution X. And before I went on, I looked at this and I see that there are 3 equations here and 4 unknowns, x1, x2, x3, x4, which means there are more unknowns than there are equations, so there is a non-trivial solution. So I can say, just by looking at this, that this set, the set of 4 vectors, is dependent. And that is sufficient to answer the question. However, I did want to find the non-trivial solution. So here I put the augmented matrix and I row reduced it until I got 1, 0, 0, negative 2, 1, 0, 0, negative 1, 1, 1, 1, 0, and 0, 0, 0. So what this told me is x3 is equal to 0. Oh, x4 is free, x3 is equal to 0, and then x2 is equal to x3 minus x4, which since x3 is 0 is just equal to x4, and x1 is equal to 0 plus 2x2 minus x4, which is equal to, plugging in for x2 is equal to minus x4, I get minus 3x4. So our solutions look like they're all separating my factors of x4. I have minus 3 in the x1 position. I have minus 1 in the x2 position. I have 0 in the x3, and then x4 I have 1. So all my solutions are multiples of minus 3, negative 1, 0, and 1. And I can verify this solution, and I'm just going to take, x4 equals to 1. So I'm going to check out the solution, negative 3, negative 1, 0, 1. So I have negative 3 times my u vector, which is 3, 2, negative 4. My minus 1 times my v vector, which is negative 6, 1, 7. My 0 times my w vector, which is 0, negative 5, 2. And then my 1 times my z vector, which is 3, 7, negative 5. And I set that equal to 0, 0, 0. Well, actually, I don't set it equal to 0, 0. I need to verify it's equal to 0, 0, 0. But here I have negative 9 plus 6 plus 3 will give me 0 on top. I have minus 6 plus 1, no, minus 6, oh, minus 1, minus 6, minus 1, so that's minus 7 plus 7 gives me 0, and here I have 12 minus 7, which gives me 5, minus 5 is 0. So I have verified that this is my solution, and this is the form of my solution. And furthermore, I can show you that I can write one of these 3 vectors in terms of the other 2. Here, remember, w is not playing a part of our solution for dependence. And I chose to write everything in terms, I guess I chose negative 6, 1, 7, because I figured I could just move it to the other side. And then I would have negative 6, 1, 7 is equal to negative 3, 3, 2, negative 4. And then I have plus 3, 5, and 3, 7, negative 5. And again, I could have solved for 3, 7, negative 5 in terms of these 2, or I could have solved for 3, 2, minus 4 in terms of the other 2. I would have had to divide by a negative 3, and I don't like doing division, which is why I chose this one. This would be a good choice as well. But here I can solve for this in terms of the other 2 vectors. I kind of summarized my last solution here. I had my matrix equation. I concluded that the 4 vectors are dependent, and then I solved for, what is this? This is v is equal to 3 times u, or minus 3 times u, plus z. And I put this up here so I can look at these 3 questions again that we had answered previously about these 4 vectors. First, we found that they were pairwise, each linearly independent, but you can see that all 4, they are, in this case, they are dependent. So even though pairwise they are linearly independent, by the time you get to 4, you can see that one of the vectors is a linear combination of the other 2. And then last, this other question we had answered, when we were trying to determine if the four vectors were linearly dependent, is it wise to check if, say, W is a linear combination of U, V, and Z? And the answer was, if it's not a linear combination, it doesn't mean everything is dependent or independent, because as you can see in this solution here, which we found the four vectors are indeed dependent, W did not play a role in our determination that the four vectors were dependent. And this last problem I'm going to relate to our previous problem. So the last problem is, suppose that we have three vectors, v1, v2, v3, that are linearly dependent. So it's a dependent set. And v4 is another vector in Rn. Show that v1, v2, v3 with the addition of v4 is also linearly dependent. And the thing I wanted to relate to our last problem is we had our four vectors, and we showed that three vectors had this dependent relation, that v was equal to minus 3u plus z. So w wasn't involved at all. But I did say, because these three had a dependent relation, then that w, the four vectors, including w, was also dependent. So this is sort of the proof that you can just throw in extra vectors. Once you have a dependent set, you can just throw in extra vectors and it'll still be dependent. So your problem, or the problem for you to try, is to prove this statement. Suppose v1, v2, v3 is a linearly dependent set in Rn, and v4 is also a vector in Rn, then show that v1, v2, v3, v4 is also a linearly dependent set. To start this proof, I'm going to start with our given, our hypothesis. So we're given that v1, v2, v3 is a linearly dependent set. That means there exists x1, x2, x3 in the real numbers that are not all zero, such that v1, x1 plus v2, x2 plus v3, x3 equals 0. And this comes from the definition of linearly dependent. If they're dependent, there is a non-trivial solution to this equation. Because now I want to talk about v1, v2, v3, v4, I want to add v4 to here. And I can do that by adding v4 times x4, where x4 is equal to 0. Certainly it's still the same equation when I multiply x4 times 0. So I have v1, x1 plus v2, x2 plus v3, x3 plus v4 times 0 is equal to the 0 vector. And remember, for x1, x2, x3, not all three are 0. So where x1, x2, x3 are not all 0. So that implies that v1, x1 plus v2, x2 plus v3, x3 plus v4, x4 equals the 0 vector has a non-trivial solution x, x1, x2, x3, 0, where x1, x2, x3 is the non-trivial solution to our equation v1, x1 plus v2, x2 plus v3, x3 equals the 0 vector. And remember, this has a non-trivial solution because v1, v2, v3 are linearly dependent. And therefore, since this equation here, this linear equation here, has a non-trivial solution, that means the set v1, v2, v3, v4 is linearly dependent. So that is it for this video. Thank you for watching.